Hi everyone! Today let's talk about sessions 8.4, Dijkstra's shortest path algorithm. To find the shortest path from some point A to some point Z on the graph using a method designed by Edgar Dijkstra from Netherlands. So this is the algorithm to find the shortest path between 2 points on a weighted graph. Do you remember we did some examples in the previous sessions? Okay, we have a weighted graph and we want to find the shortest path. What we did before, we list all the possible paths and we calculated all the lengths and then we compare and pick the minimum length. Okay, and then so that way is really time consuming because let's say if we have arranged like 3 letters in the boxes, we have 6 possibilities. If we want to arrange 4 letters in the boxes, we have 24 possibilities. And next, to arrange 5 letters in the 5 boxes, we can have 120 possibilities. And that's really a lot as we increase the number of vertices. So that's why today we introduced an algorithm, the Dijkstra's algorithm. It can help us to find the shortest path. Okay, so the process involves labeling the vertices. At some point, some vertices have temporary and the others have permanent labels. Okay, so we're gonna each steps we're gonna label the vertices. Okay, so the algorithm finds the length of a shortest path from a vertex A to a vertex Z. The algorithm will have entered the weights of the edges, the first and the last vertex, and the length found. The weight of edges ij is w of ij greater than 0, and the label of the vertex x is L of x. So this is the length of the shortest path from A to X. So at termination, LZ is the length of the shortest path from A to Z. Okay, so here is the algorithm. For the first steps, we label LA is 0. So that is our starting point, right? So the length of the points to itself is 0. Okay, and then for all the other vertices, we label LX is infinity. Okay, so this is the first step. And then let T be the set of all vertices. So T is the set of all vertices whose shortest distance from A has not been found. So you can think of this as like the set of like vertices with temporary labels. Okay, and then next, we pick, okay, so we had, now you can see the terminal points is in the set T, so we choose vertex in T with minimum length, okay, and then we move this vertex from this set T because we know it has minimum length, so we can this label we can fix. It becomes a permanent label. Then we can remove V from the set, and then you look at the vertex adjacent to V, and then you find out what are the new labels. Okay, of the X. Then you compare which one is the minimum. The minimum one, you're gonna set that label to be a permanent label, and then you can remove that vertex from the set. So those are the step 2, and then we repeat the process of step 2, and then until we reach the vertex Z. Okay? So don't worry, we'll go over some example and then it can help you to understand this algorithm. Okay, even though it looks like a lot of symbol to you, but trust me, just be patient, and as we go follow the examples, then you will understand what it means. So here we have some notation. The vertex which uncircled have temporary labels. The circled vertex has permanent labels. So after we've assign a permanent label to a vertex, we circle it. Okay. All right. Let's start. Let's look at this example. We want to find the shortest path from a vertex A to a vertex Z. So this is A. A is right here. Z is right there. So A is our starting point. Okay. And Z is our terminal point. Okay, terminal vertex. So far, so good, everybody? Alright, so let's start. So here I make a table, and then for each step I can show you what I do in that steps. Okay, so first step, label. Okay, so this is step 1. Okay, so label A 0. So L of A is 0, and then L of other vertices to be infinity. So this is the first step. Very simple, right? And then next, which one is the minimum label? Of course, the 0 is the minimum, right? So step 2. Let me see. Okay, so this is step 2. Because LA is minimum. Okay, so LA is minimum, of course, because it's 0. So circle A. Okay, so circle A, you see here, we circle A. Next, we want to look at the vertices that are adjacent to A's. So adjacent to A. What are the vertices adjacent to A? Well, that is B and F, right? So we have 2 vertices adjacent to A, B and F. Then now let's figure out the length of B and the length of F. Okay, the length of B is, you see here, we get this guy, the length is 2, so we have the length of B is 2, and the length of F is 1. So length of B is 2, length of F is 1. Okay, which one is the minimum? So next steps, we can see LF is minimum. So when we talk about which one is minimum, we look at the uncircled vertices. You see, within those uncircled vertices, we have B label 2, F label 1, and all the other vertices label infinity. So the minimum one is LF is minimum. Then we circle F. Okay, so once we circle F, it means the label of F is fixed. It is permanent. Okay, then now we continue. Okay, what are the vertices adjacent to F? Well, adjacent to F, and you don't count A because A we already fixed. We're talking about the vertices that are unlabeled. I mean, the vertex doesn't have a permanent label. Okay, so those are D and G. And then LD and LG, let's see. What is LD? Well, D is right here, yeah? So it's 1. Add 3, that's why we get 4. Oops. Okay, so that's why we get 4. How about G? G is right here. We have 1 plus 5. That's why we get 6. Okay, we're talking about the length of the path from A, start with A. So A and then F and then G. So that is 6. Okay, now we compare the vertices with temporary labels. Which one is the smallest? Okay, no, you're not just comparing 4 and 6. You're comparing the B as well. The label of B is 2, so that's why this guy is the minimum. Okay, so that's why we need to circle it. So the next step, LB is minimum. So each step you're comparing the labels of all vertices in the set T. So T is the set of vertices with temporary labels. Okay, so B is minimum, so we circle B. And then we look at what are the vertices adjacent to B. Well, that is, we don't count A, right? Because we already have A circled. So A has a permanent labels. So we have D and E and C. Okay, let's figure out what it is. So we have L, D, L, E, and L, C. LD, we already have a label for D, right? It is 4. So when we talk about LD, we're comparing the minimum of the original, like temporary label, and the path goes through B. So B, the label of B is 2, and then D is like this guy. So 2 plus 2 is also 4. So we still have the same label, okay? And E is new, so B has LB is 2 plus the edge between them has weight 4, so we have 6. C we have 2 plus 2, which is 4. Okay, so D we still have 4, E we have 6, C we have 4. So far so good, everybody? Okay, now we want to compare. We want to compare the vertex that with temporary labels. Which one is minimum? Well, here we have 2 minimum, right? We have the C and D, both of them have labels 4. Okay, so let's put it down. Okay, so here, step 5, L, C, and L, B are minimum. We circle them. Okay, I mean D. Okay, oops, draw better. Okay, now circle them, and then let's look at C. Adjacent to C are we don't count B because we already circled B, so E and Z. And then L, E is, do we have E already? Yes, we did. That's 6. So we want to have pick the minimum of 6, and then when we go through the C, we have 4 plus 3. Okay, so the minimum is still 6. And then LZ is label of C, which is 4 plus 1, it's 5. Okay, and we also need to look at adjacent to D. So adjacent to D, we have just E, right? And then LE is what we have for now, the 6. And then when we go through the D, we have 4 plus 4. Oh, that's 8. So the minimum is still 6. Okay, now see, G, we have the label 6, E label 6, Z label 5. Which one is the minimum? You can see minimum. So if we call it step 6, LZ is minimum, then we can circle it. Okay, and then we're done because Z is the terminal point we want to get through to get we want to have a shortest path, get to Z, and then now we have find. Okay, so we can end the process, and LZ is 5. And what is the shortest path? The shortest path. Okay, so when you find the shortest path, you can go backwards. Look at your Z. How do you get your Z? Well, you get your Z from C, right? So that's why that's C. How do you get your C? Well, you get your C right here. So you get your C from B, okay? And how do you get to B? Well, you start with A. So far, so good? Okay, so then we have found the shortest path. Okay, isn't it nice? So it just need to separate it into like quite a lot of steps, and then at each step you're gonna compare all the labels of the vertices with temporary labels, and then you find the minimum and then circle it to make it as a permanent label, and then you're gonna look at the vertices adjacent to that vertex. Okay. All right, let's do more example here. Okay, so this is another example. We want to find the length of a shortest path from A to Z. Okay, so in this case, we want to label the vertex with the name of the vertex from which it was labeled. Okay, so instead of just the shortest path, the length of the shortest path, we also want to label the vertex from which it was labeled. Okay, so step 1. Okay, step 1, LA is 0, L others is an infinity. Okay, and minimum is LA. Circle it. Let's just combine them together, right? So far, so good. Okay, so we circle it, and then we look at the vertices that are adjacent to A. So they are B and D, right? So B and D. Then what is LB? What is LD? So LB is so we want to label with the vertex that is from. So B is adjacent to A. This is where it's formed. And what is the length? Okay, that's the 2, right? LD is also from A, and what's the length? Well, that is 1. Okay, so now we have labeled them. Then which one is smaller? So minimum is LD, right? Then we circle D. Okay, so we circle D. And then what are the vertices that are adjacent to D? So that is A, but we already circled A, so we get E, right? What is LE? LE is from D, right? And then we have our label of D 1 plus 1, so we have D comma 2. So far, so good, everybody? Okay, now which one is minimum? Well, you can see here we have B and we have E. They both have length 2, right? So we can say minimums are LB and LE. We circle both of them. Okay, let's continue. Oh, why they move here? Okay. Alright, so we circle B and E, and then we look at vertex adjacent to B. Oops, something wrong with my word. Okay, let's see. Okay, this takes some time. Can I move it? All right. Okay. So adjacent to B is the vertex C, right? And it's also because we're looking for the uncircled one, so C is the only vertex that is adjacent to B and is not circled. So LC equals it is from B, and then the length is 2 plus the edge between them 3, so we have B comma 5. And then we look at vertices that are adjacent to E. So adjacent to E, that which is uncircled, that is Z. And what is LZ? LZ is from E, and then we have 2. The label of E is 2 plus the weight on the edge between them 2, so we have E4. Okay, so Z has E4. All right. So far, so good, everybody. Okay, now we have the uncircled one is only C or C and Z. So of course, Z is the 4 is smaller. So that's why let me put here. So minimum is L Z. Okay, then we can circle the Z. Well, once we circle the Z, we're done because this is the terminal vertex. Okay, and so we have LZ is E4. The length of the shortest path is 4. And what is the shortest path? Well, we can read from the label. So Z, you can see, is from E. And then let's find the E. Oh, we can see from the picture here. E, you can see E is from D. And then D is from A. And so when we, this is the good thing about listing the vertex which is from. So it's better to, if we do this, then we can, when we write down the shortest path, we know which vertex it is from. So far, so good, everybody. Okay, these graphs are still easy. So here are some more examples, which we're not going over in class, but feel free to play with them after class and have fun. And I want to say it is possible that you in the process you might get LZ. Let's say if this is Z, in the process you might get LZ at some point, but if it's not the minimum in the remaining uncircled vertices, then you cannot end. You must end when you have LZ is the minimum label. Okay, then you can circle it. It become a permanent label. Okay, so what I mean is it possible maybe you go this way, you go this way at some point, and then you realize, okay, then this is the minimum label at that age, so you want to go back to this way and then eventually get to this point. It is possible. So as long as the LZ is not the minimum and it's still a temporary label, okay, then you have to continue the process until you have LZ be the minimum among all those uncircled vertices. Then you can end the process. So you have some examples in your homework as well to about like what I just said. Okay, you can also play with these examples after class. Instead of starting with A and Z, you can start with, let's say you can start with here and then you want to end it here. Okay, or you want to start here and then end it here. It's not necessary like start with A and end at Z. Okay, it could any two vertices, you can also find the shortest path between them. So far, so good, everybody. Yes, there are a lot of graphs here you can practice. Okay, and if you have questions, feel free to ask me in class or office hours or email me. Have a nice day. Bye.